All right, hi geology students. Today we're going to talk about Earth's interior. So to do that, we have to look at some background info on waves, some of which you probably already know. But in geology, we're going to talk about, in this class, P waves and S waves. Now first we're going to focus on the P waves. Now P waves, P stands for primary, because these are the first waves that we'll feel after an earthquake, because they're the fastest moving waves. But that's where the particle motion is parallel to the wave motion. So you can see in the animation here, it's like a compressional wave. Okay, so you can see how the wave is moving its way through. Now, what I want you to do is I'm going to show you a picture here of an earthquake happening on Earth, and I want you to look at the P waves and try to make some observations. All right, here you go. Now, for this, what I want you to look at is Earth's surface observation. So, if you are standing on Earth, like these two guys are, maybe what are some things that you could determine based on the waves? Okay, so what you should have seen there is, or noticed, is that we have these shadow zones, okay, where the waves, for the one guy that was standing down here, right there, that he wouldn't feel the waves. So this guy, maybe you could say that, well, if you look how we sense the waves as it takes a little bit more time, right, the further away you get from the earthquake. But this guy standing over here didn't feel any waves. Okay, so that would be one potential observation. Okay, so these P waves have a shadow zone, right, where they're not detected. From that, we could say, well, something is preventing those seismic waves from reaching those areas, which then obviously goes to the question of what would cause these shadow zones. So look at this again and see if you can figure out why there are these shadow zones. Okay, and what you should see there, or what you should have said, is the reason we have those shadow zones is because the waves are being refracted and reflected as they pass through Earth's surface. You can see if we have the earthquake, the focus of the earthquake occurring here, some of those are being reflected right off to the surface, but then some of them are being refracted or bent as they're going through the Earth's surface. And as a result of that, you end up with this shadow zone here, where we're not detecting any of those P waves, right? So if we look at what would be the cause of that refraction, if you remember back to your physics class, it's because of density, right? So we have in a substance that has a uniform density, right, or one that isn't very dense, those waves would be able to pass straight through without any refraction. But when there's a change in density, those waves get refracted, and that's what actually is going on here as we pass into the Earth. Okay, so here's that animation again, okay, and just so you can kind of see how this works. So these waves up here are being refracted, right? So they're being, and some are being reflected as well. So they never get to this area. And then the ones that would maybe come over here and hit the side of the Earth, they hit something on the inside of the Earth, right, that caused them to be refracted again. Okay. Now the other thing I want you to look at here is the velocity of the waves. Okay, so just look at the speed of these waves. Okay, do you notice anything with the speed of the waves? Now hopefully what you saw here is, do you see how the waves slow down in this middle section, but they speed back up again here? Okay, so we have kind of a higher velocity, and then they slow down, right, through this middle section, and then they speed up again. Okay, so that's our observation that we would make there, is that those P waves slow down, right, in one section, and that's what this graph is showing. Now again, we don't, as we're working our way through this, we don't really know what's going on inside of the Earth, but we are making these observations, right? We're trying to draw conclusions, but the P wave moves along, but it slows down a bunch when it gets to this area inside of the Earth, right? So if we're looking at another, trying to analyze what's going on here, what would cause waves to slow down? Okay? And what we find is that we know from other experience that the stiffer the medium is, the faster the waves travel. Okay, so if you've got a medium that is, for example, a solid, right? Solids are going to have a higher velocity. Of the waves are going to be able to travel through at a higher velocity. But the less stiff substance is, okay, or the less rigid it is, a rigidity, right? The less rigid it is, those waves slow down. Okay, so that's going to tell us something. So just for now, hold on to that thought. We'll come back to that here in a little bit. Now what we're going to focus on are these S waves. S waves, S stands for secondary. So if you look at S waves, it's kind of a transverse wave. Okay, so you may be a little bit more familiar with this type. So let's look at these waves and see what we can see. All right, so right away we see something different is happening with these S waves. Okay, so for that observation, yeah, we see this big shadow zone now. So those S waves get blocked by this thing on the inside of the Earth, right? But we are able to detect them on the edges here. So again, another observation is that these S waves, again, are blocked by something causing this big shadow zone on the backside of the Earth. And if we're, again, trying to figure out what could possibly cause that shadow zone. And with this, we know that S waves need a medium that's rigid enough to propagate. Okay, so which means that if you have a substance that is lacking rigidity, such as a liquid or a gas, S waves cannot travel through those. S waves basically they need a solid type material to be able to move through. Okay, so this is kind of showing that idea again. So here's your P waves. See how they slow down, right? But then here's the S waves. Boom, they get blocked, right? They stop. So we are going to be able to draw some big conclusions from that. Okay, here's a couple of animations showing, again, same idea. So your P waves are the dark blue. They're able to pass through versus the S waves, right? You're going to see the light colored blue get blocked right there. They're not able to come through. Here's an actual earthquake. Okay, this was 2002, I believe, up in Alaska. A big earthquake, almost an 8 on the Richter scale. But again, same thing here. So this is actual data, right? And the cool thing now is we've got these supercomputers that can calculate all this and figure this all out. But the blue, I'm sorry, on this one, the blue lines are the secondary waves, right? They're getting blocked, but then the red P waves are able to travel through. But you can see how, and this is the seismic graph up on the surface that was actually measuring these. This animation on this side is showing the surface waves. Now those are a different type of waves that we won't really focus on too much in this class. But again, here's some real data showing essentially what we just looked at with those animations. So here's some big conclusions that we can make from that. Okay, by looking at these seismic waves. Okay, we know that even though we can't get down in the Earth that deep, we know that Earth has different layers with different densities, an increasing density as we go down towards the center of the Earth. Second thing is we know that there is a layer down there, okay, we call it the outer core, that's liquid. Okay, because those S waves can't go through them, the P waves get refracted even more because of it being a liquid down there. So those are two big conclusions. Okay, now from that then we can kind of put together this picture of the Earth. And we know the Earth has these 4 layers, inner core, outer core, mantle, and a crust. So let's go just through some details on each of these. The inner core is solid. We know that because those P waves increase in speed down there because it's a solid and it's very dense. And we believe it's primarily iron and nickel. You don't need to know what the composition is. I'm just telling you just so you have an idea. Okay, that next layer is that outer core. Now the outer core, like we said, is the one that S waves cannot travel through. So that tells us right there that it's liquid. Okay, so it has to be a liquid material. And the belief is that, I gave you some elements here that are down there, but we believe that if there's sulfur present, that actually lowers the melting point, which allows it to be a liquid. Even though it's under tremendous pressure down there, it still is behaving as a liquid. Now the mantle, okay, is most of Earth's volume. Okay, you can see it's a thicker layer, so it's making up most of the Earth. But this is a big thing, guys. It is solid. It may behave like a fluid, so it's moving, right? But it is a solid material. A lot of people think the Earth is filled with lava, right, or magma. But it's solid material that's down there, primarily because of so much pressure down there, and that's able to keep it as a solid. And then as we get closer to the surface, right, then we start to see some melting because we decrease the pressure. So what we end up having here is up near the surface, we call it the asthenosphere, the mantle becomes more plasticky, right, a little bit more fluid, okay, but still a solid, but it still kind of has this fluid property to it. And then we get up to the top and we're nearing the crust where it starts to get rigid. And the last layer up on the surface here is the crust. We have two types of crust. One is continental crust. That's where the continents are, right? And you'll notice here it's mostly granite. Okay, we've talked about. Now there's obviously other rocks as well, but if we just want to generalize, we'll say that it's granite. And about 35 kilometers thick. Again, you're not going to be responsible for these little nitty-gritty details. But oceanic crust is, and notice here, it's more dense. That's a key idea, is that the ocean crust is more dense. And it's basaltic, which we've talked about already, so it's basalt primarily. And you'll notice too, it's much thinner. Okay, so the ocean crust is more thin and more dense. So we've got Beavis and Butthead here looking at this animation showing this oceanic crust right here, the basalt thinner, versus the continental crust here, mostly granitic, and it is thicker, right? And Butthead says that, well, that's subduction, and then Beavis is saying, no, that's convection. Which one of those guys is correct? Is this animation showing convection or subduction? Maybe a new word for you. Yeah, if you look at that one, Butthead has it right here. That is subduction. That's what we call it when that oceanic plate, which is more dense, is going underneath the continental plate. So that is called subduction. Some cool facts here on the side. Earth's overall density is 5.5, but remember, we're getting more dense from the surface going down to the surface. Even though we're changing, from solids to liquids to solids, the overall density is increasing as we're going downward. So there's the diameter of the Earth, 12,000-ish kilometers. But here's an interesting thing. So our mines that we're able to dig down only go down 3 kilometers, and we've been able to drill or bore down to 12 kilometers. But again, we can't even get close to the center of the Earth. So any movie that's showing us going down to the center of the Earth, we are so not able to do that. Not even close, because again, the density and the pressure and the temperatures down there. All right, if you guys have any questions, shoot me an email, rewind, watch some of the video again, or stop me in class. Have a great day.